Hello friends, so the topic of my discussion is today Poynting theorem, Poynting vector, and I will describe some numerical examples on the electromagnetic wave with the time Everest Poynting vector and energy flow. What is the physical significance of it? And you will find very common things this in your competitive exam, that you will often you are asked to solve the problems on the Poynting vector, Poynting theorem, time Everest Poynting vector. What is the energy flow in common BSc and MSc? So you must have remembered that in one of my previous lecture, electromagnetic wave in the non-conducting medium, I have talked in brief about the Poynting theorem and the Poynting vector. What is this notation? But in my lecture, this one, I will just step by step, I will show all of the calculations and the derivations, that how the Poynting vector will come, what is its physical significance, so you can solve any questions in any competitive exam. Okay. So let's start, friends. And if you have any question, you always welcome to just post it on my YouTube channel so that I can help you with my knowledge. Okay. So first, Poynting theorem. What is it? It is like a power theorem for the electromagnetic field. Suppose we are having some transmitter and the receiver systems. Energy is flowing through transmitter to receiver. So whatever the electromagnetic flow energy or the flow, it can be physically characterized by this Poynting vector or Poynting theorem. So we'll see it now. How we just reach to the Poynting theorem with our basic equation is the Maxwell's equations. You know, this is the Faraday's law, this is the Ampere-Maxwell law, and what we do just from vector calculus, we just do the divergence of that E cross H. When you do that, you're left with H dot curl of E dot curl of and that sorry, it will be E and it will be H. So when the divergence of that quantity, divergence of E cross H, whenever you replace the value of curl of E, that curl of E will be del B del T, and the curl of H will be del D del T. And so you are having effect, you are left with that equations E dot J H dot del B del T E dot del D del T. You know, for the linear medium, that D is equal to epsilon E, so you replace that, it will be E dot del E del T H dot del H del T, and there will be a constant term of epsilon and the mu. So from this equation you will reach to this equation with the implementation of that things. I request everyone to just do this calculation by hand. Just like my previous lecture, I have always urged you everyone, please do the calculation with your own hand so that you could understand all the steps to derive the equation. So you can, you know, this del del T of H square means 2 into del H. So there's the half term introduced that in there, so this half term comes from there, and again you just replace E is equal to D by epsilon and H is equal to B by mu, and you can reach to this equation from this to this using that vector, using that derivative. So the half term comes there from. So when we integrate this equation and we just apply Gauss divergence theorem, what we can get, so for integrating this equation over a volume, it will just convert the volume integral into the surface integral. Suppose a volume is just volume is just enclosed by the surface, and you can convert the surface integral to volume integral and the volume integral to surface integral. And this volume integral E dot J dV, this term, and there will be another term in the right hand side minus del del T of integrate over volume, half of this term. So let's see physically what this term signifies, and some rearranging, after some rearranging we will come to this conclusion. Now there is another term you in the next, my previous slide is E dot J. So let's find physical significance of the term E dot J, what it physically means. You know that if in the electromagnetic field there will be rate of work done with del dw dt on the charge of dq. So how dw dt means rate of work done. It will can be written as force dot the velocity. So you can, and always you check one thing students, please, dimension, you check the dimension of the rate of work done, dimension of force, the dimension of the velocity. So this V, this dq means this force. You know, in the electromagnetic field, the force is dq into E plus V cross B. This is the electric force QV, and this is the magnetic force dq into V cross B. So in addition, this will be that term. And the velocity of the charge is V, and the charge current, this is J, is equal to current density, means charge density into velocity. So when you replace this force in the electromagnetic field with the velocity, you will reach to this term rho dv E dot V. Okay, so rho into V means the rho into, well, it will be J, this rho into V, and there will be electric field, and there's a volumetrical. So you reach to this term E dot J dV. In my previous slide, you see that there is a term E dot J dV that represents the rate of doing work on the charges in a volume V by the electromagnetic field. So, and there is another charge half of E dot D and B dot H. So there's a quadratic term in E and quadratic term in H. You know, this is the total energy density in the electric field. This is the total energy density in the magnetic field. So this is the electromagnetic field. This is the total energy density, and what it represents. And when you from there, same in the linear medium, you replace d by epsilon E and b by mu h. So you reach to this term. So what we'll get, this term minus del del T of V minus term indicate the volume is decreasing. Electromagnetic energy is decreasing, and it is decreasing in a volume of V. So this is the total electromagnetic energy, the rate of decrease of electromagnetic energy in a volume. Integral does represent that. And now, whenever you are doing something calculation in physics, always remember one thing, friends. Just dimensional, check the dimension, what the dimension means. Here I have proved this. This is the rate of work done. So you have to think whether it is right or wrong. And you can check this E. The E means electric field. That means voltage divided by the length. That means volt by M. And J means current density, current per unit area. So volt into ampere means VI, means the power, and the denominator term is the area into length, means the volume unit. So this E dot J is the unit of power per unit volume. That means the rate of doing work per unit, rate of doing work is the power, and it is decreasing in a volume V. So you can cross check the term E dot G, what this physically means. Yeah, so this is the Poynting theorem again. This is the term E cross H dot ds. This is the term which is the rate of doing work by the electromagnetic field, and this is the term, this is called the electromagnetic energy is decreasing in a volume V. So this, the whole thing is called the Poynting theorem. This is nothing, basically you can see this is the energy conservation rule. Whatever the energy flow up, outflow of energy, because in the right hand side there will be outflow of energy, so in the left hand side this is the rate of doing work or the in a volume V. So this term E cross H dot must be something that is real, that can be relatable with the rate of outflow of energy through a surface particular. This is ds. Okay, so you can see you don't need to remember this equation, only remember the energy conservation things, that this right hand side is decreasing in a volume V total energy, and there will be E dot J dV. That term is the rate of doing work. So there must be another term compensating, which must be the rate of flow of energy. So this is the rate of outflow of energy, what I have told, and you can specify this is this Poynting vector E cross H. Someone just in many books, textbooks, or in many lecture, you can see that it is represented by P, so you can represent by P or S, it is up to you. But this is ultimately you have to remember whenever you are just appearing in exam and you will be given the term, you have to remember this is a Poynting vector, the amount of energy flowing out per unit area per unit time, and there is a unit watt per meter square, the flow of energy simply. So this is the rate of outflow of energy through the surface summing with the rate of work done on charges, that's E dot J dV E cross H dot ds, and the rate of decrease of electromagnetic field energy, that is just equating with the term, that means the half of epsilon E square and mu H square. So this is our complete derivation of the Poynting theorem and its physical significance. Now let's solve some numerical problem. Very basic problem to start with. It's a very simple problem, nothing to do, just you just replace the terms. You are having an electromagnetic wave. This is the electric field. In the electric field of an electromagnetic wave, this is the sinusoidal things, sine terms, 50 is the amplitude, and you have to find the energy. This is contained in a cylinder cross-sectional area with the length along the x-axis. So you know the energy density or the energy that you are need to require, that is in electric field, that is proportional to the electric field amplitude square, half epsilon e square. This is a free space, so if epsilon 0, you replace the terms and you get the, and it is the energy density, energy per unit area in volume, so that if you multiply it with the total volume, you will get the desired energy, that is 5.5 into 10 power minus 12 joule. Basically, so Poynting theorem is the principle of the conservation of energy or nothing else. So now, whenever you are doing the Poynting theorem numerical example, often you are asked to solve the time average Poynting vector. At every point, what will be the outflow of energy? So to solve that, you need to solve the time average Poynting vector. So what is really time? What really the time average Poynting vector? Let's see. So there's some smiley, and this is the electric field. You know, supposing some sinusoidal variation, and we add some phase terms. Electric field phi is in the x direction. Magnetic field, that phase associated with the magnetic field, you can take it as a phi h. With the same frequency, they are oscillating electric and magnetic field harmonic approximation. This j cap means y direction. So now when you are doing the electric field at a particular time t, that means instantaneous electric field, so you have to take the real part of that thing, a real part of magnetic field, that is instantaneous E and H value at a particular time. So now the particular time, that means when you take the real part, e to the power I, it will means cos, e to the power I theta means, you know, cos theta plus I sin theta, so it will be a cos term, only real part. We extract the cos term, and when you extract the, after extracting the cos term, you just derive the you just calculate the Poynting vector E cross H. That means E0 H0, cos of this term and the cos of magnetic terms, and I cross J, I x direction, y direction. So basically when you are taking this E0 H0, cos A cos B, so you have 2 cos A cos B, you know the relation from trigonometry, so you transform it in a sum terms, cos of A minus B minus cos of A plus B. So this term comes from 2 cos A cos B, so here 2 is just in the denominator. I cross J cap means K cap in the Z direction. Basically if it electric field in the X direction, magnetic field in the Z Y direction, and Poynting vector will be in the perpendicular Z direction by the vector rule, curl. Now when you have to find the average of that, how you do, you just integrate it to 0 to 1 time period and divide it by this time period. Okay, so you do the calculation in your hand. What do you get if you integrate this? This is the constant term, you can easily see. When you integrate this over a complete time period, 2 pi by omega, what will get? Cos of integration of cos will change it to a sine. So whenever you are having sine of 2 pi, means it t is equal to 2 pi by omega, so sine of 2 pi, this term will be estimated to be 0. So we are left with that only E0 H0 by 2, and this t integral t and t will just nullify, and you are left with only cos of phi e minus phi h dot k cap. So you'll see, in order to have energy flow, the electric and magnetic field will have to be in a perpendicular direction. There will be no phase quadrature. Poynting vector is in the direction of the wave propagation, means k direction. This is the k cap, means z direction, average. So it is our average Poynting vector. When you are having the equal phases phi e and phi chi, means magnetic field and electric field have equal phases, so cos of 0, so any term with cos 0 means 1, and you are having that we're left with the Poynting vector half of E0 and H0. This formula is very important, and often you will be using that formula. In my next slide, I will be using that formula of average Poynting vector. but in general you are having some common term in which you have to express that average pointing vector. So I will get it. This, how you can write this term cos of phi phi h. So you take the real part of that electric field and the complex part of that magnetic field. So this I omega t, this will cancel each other, and this will be minus e to the power I phi h, it will be I phi e. So e to the power I phi e minus I phi h, when you take the real term it will just convert it to cos of phi minus phi h. In general you can find average pointing vector is the half of real part of E cross H vector, means electric field into magnetic field star. Okay, so this term, this is a very important thing. You need to remember this, what is the average pointing vector. We'll be using that formula in our next slides. Okay, now we see our next numerical example. What is that? You have to find the energy stored in the length of laser beam operating at 4 milliwatt. So I again just request to every one of you, whatever the derivation terms, you do it by own hand, and after that if you find the physical significance, then you just start solving the numerical question. It is very easy. So first I will start in that length. The time to move through this distance will be this 60 by c. So the energy contained in that 60 centimeter, it passes through the cross section of the beam in that t second. Okay, now the energy passing through that second will be that 4 milliwatt is the power cross that time. Okay, this power means per unit time. So you multiply with the time. This will be the energy stored, total energy stored. Okay, so unit wise you can see this is the energy. This watt means joule per second. For your convenience, I have just introduced that. I have just written that or introduced that unit so that you can see it, visualize easily. That you will get this point vector or the total energy flow in terms of the total joule. Okay, yeah. Now I'll the third numerical example. You have to find the strength of the electric field at a distance 10 meter from the 60 watt lamp. From 60 watt means here you are given the information of the power joule per second. So you know the intensity, or you can find tell it the time versus pointing vector is just, you can get that this total power per unit area 60 by 4 pi area, because you assume this lamp to be at the center. This is source of energy, and around that you can assume a spherical surface which is radiating energy. So within that spherical surface the power per unit area is that S average, and you know this S average is nothing but E0 H0 by 2 time average pointing vector. So you can write it in that way. RMS value is just like a maximum value divided by root 2. So you are required to just estimate the strength of the electric field, means the RMS value, not the maximum amplitude. So after just replacing that, substituting that H0 B0 by mu 0 and mu 0, you know this is from, if you don't find, you can if you can't remember this equation, you will go to my slide electromagnetic wave velocity, electromagnetic wave velocity, that I have introduced this how to get this term. This is mu 0 epsilon 0 means 1 by c square. So after replacing that, you will reach to this term S average means half of c epsilon 0 e 0 square, means the RMS value you can get from that with the time average pointing vector divided by this equation. So after substituting all the terms, you will get that the RMS, the strength of the RMS value of the electric field comes out to be 4.24 volt per meter. So hope you have understood this numerical example. You do it by own hand and you follow it so that you can get a rough idea of this, how to calculate this pointing vector. Okay. There will be another example I have done for you. So this is the intensity of the sunlight reaching the surface of the earth is 1300 watt per meter square. So you are having power per unit area, and you have to find the strength of the electric field, means same RMS value of the electric field. So what information you are having? You are having the information of the average pointing vector, and Always you just for time average Poynting vector, this is the harmonic variation I've shown in the calculation or the derivation of my time average Poynting vector. This is a harmonic variation. So S average is generally ERMS cross HRMS. Now you have to replace this HRMS value. Now you know the maximum electric field is just c velocity of light into V0, and you have to replace the c by 1 by root over. This is the velocity of light. You can follow from my slide, and b means mu h. So after substituting this, you find RMS value of the electric field is equal to mu by epsilon RMS value of the magnetic field. In general, this mu by epsilon is can be called as the intrinsic impedance of the medium. That means, and you can relate to it in my last chapter. If you follow my last chapter, in my last chapter I have just discussed about the electromagnetic wave in the conducting medium. So there you will be having a term Z. You can relate the Z, that means the resistivity. In geophysics you often use the term, and the physics you can just the standard notation of the but this eta and the Z are almost equal. That means the resistivity or the intrinsic impedance, that is E by H, and tensorial form you can find E by H eta intrinsic impedance. Standard value is just like 377 ohm, means the unit is in the resistance unit. Okay, what I told. So substituting that HRMS values, you can get that ERMS value is means S average root over mu by epsilon. Okay, and now this mu 0 is this term 4 pi 10 to the power minus 7, and epsilon 0 is the term like 8.854 10 to the power minus 12. This S average, you are already having the information of the average Poynting vector, that is 1300. So you don't need to divide it by the area, because it is already given in the units of area. In my last numerical example, only Poynting vector is given, total Poynting vector. So you have to find S average, you have to divide it by the area. So after substituting all these, you will get this RMS value of the electric field is 337, means the standard value of the intrinsic impedance. Okay. So this intrinsic, the total RMS electric field comes out to be 700 volt per meter. So this is the standard things. You can follow this mathematics this in your exam or the competitive exam, like things often you will be asked to solve the problem like this. So only you have to remember our average Poynting vector, RMS value of the electric field with the maximum amplitude, and this term is given because always you derive this average Poynting vector with the harmonic variation, and you can get whatever you have required to derive. You will get the term either HRMS or the ERMS. You will be asked to derive strength of the electric field or the strength of the magnetic field. Okay, so I hope you people have got a rough idea of Poynting vector, energy flow, how the intrinsic impedance of the medium, and the time average Poynting vector. So like these things, so you can easily solve this mathematics or associated with the Poynting vector. Okay, and in one, please follow in physics and geophysics learning with me in the last lecture, that means Poynting vector introduction. So after following this, you just follow my this lecture, so it will be very easy for you to follow this. Now there is another example of the Poynting vector. That means that you have to find the intensity of the magnetic field. Just I have told, this is the same thing, same mathematics, only you have to find the HRMS values at a distance 100 centimeter. The radiating source of power 13 kilowatt. That means is given in the units of joule per second. So what you have to do, you have to just divide it by the area, that means 4 pi meter square with the energy 10 to the power 4. With the Poynting theorem, we will have this term, it's the intrinsic impedance, and the average Poynting vector is like half into E0, maximum value of electric field, maximum value of magnetic field, and you just substitute it in terms of H, and we get this Poynting vector is a 10 to the power 4 joule per second divided by the total area. So we'll equate these terms and nothing, you will get the maximum value of the magnetic field H0 ampere per meter its unit. Always just write the unit for your own convenience if you are solving any problem. And now this is the you are required to derive the mean value of the intensity, that means HRMS values. So HRMS can be written as H0 by root 2. So we'll get this equation. So this is the energy flow is average per unit time. So I hope you just understood all the problems, and if you are having any problem, just comment it on the YouTube section so that I can answer your all the question in my next in this week, or some I'm just giving exam just lecture on the electromagnetic wave. Later I will move to some magnetic field surveying or the geophysics. Within that, if you're having any problem, you just let me know, and don't forget to subscribe for my channel for getting notified with more updates, and turn on this bell notification icon with my channel name, Physics and Geophysics with Dr. Devajyoti Jha. Okay, goodbye, stay safe, stay healthy.